All right. Okay, folks. So today we're going to continue our discussion of degenerate perturbation theory. Degenerate perturbation theory. And we're going to discuss, I wanted to say a little bit about covalent bonding. And we're going to start hydrogen fine structure. Hydrogen fine structure. So this is the plan for today. So, and you guys can hear me okay, right? Yeah? Okay. So, all right. So let's dive into it then. Let's see. So the picture that I want you guys to sort of have in your head is, let's consider a unperturbed Hamiltonian, and you know all the energy levels. I'm drawing them here. This is energy going up, and suppose that there's some degeneracy. Some states are non-degenerate, some are degenerate. I have state number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. I got all the states, and these are the unperturbed energies going up vertical. But you notice that some are non-degenerate, but some are degenerate. They have the same energy, and so now what we do is we say, suppose I turn on a perturbation. That means that my Hamiltonian goes to this, where I know H naught, but I don't know H prime. And then I ask you, what are the new eigenenergies and the new eigenstates? Eigenenergies and eigenvalues and eigenstates of the new Hamiltonian, of the perturbed Hamiltonian. So then you would say, well, I can do that. I'll just use perturbation theory. It's really easy. And you say, I got a little formula I can plug into. We all love formulas. And so I know that the eigenenergy of the nth state, the perturbed nth state, is the same as the eigenenergy of the unperturbed state plus some corrections. And I know the corrections because we derived them. I just take the expectation value of the perturbation for the nth state. That's the first order correction. And the second order correction, I sum over all the unperturbed states except for one. And I calculate this matrix element, and of the matrix element of the perturbation, and I just square it, and I divide by this thing in the denominator, this energy difference. And that's the eigenenergy, and then the eigenstate is equal to the old eigenstate plus a correction. And we only went to the first order correction, m not equal to n. And now we have, once again, we have the matrix elements of the perturbation on top. We got the energy difference on bottom, and we got to multiply by those unperturbed states. Okay, so that's the formulas that we derived, and everything is very good. But now, if someone says, now we want to use these formulas, the perturbation formulas, but we first have to check. So before we can use the formula, we have to first do a little check. The first thing we have to do is check are the states degenerate? Or if we're looking at some state, we have to ask ourselves, is the state degenerate? And so let's suppose that we look at, for example, state number 9 here on this list to the left. Is it degenerate, yes or no?
No.
That's right. It's not degenerate. So if not, then use the formulas and you're fine. But what if I looked at state number 5 and I said, okay, now find the new eigenenergy of state number 5 on this thing to the left. Is that state degenerate? Yes or no?
Yes.
Yes, it's degenerate. So if the state is degenerate, then you got a problem. Because your perturbation theory expansion can diverge, it blows up because of the denominator, right? In those higher order terms. So you got a problem. And so we have to check. And so the thing that we have to check, we have to ask a new question. If the state's degenerate, then we have to check to see that we have to ask ourselves, does the off-diagonal element, somebody's making noise out there, please mute yourself. All right, I guess I'm gonna have to try to see if I can mute you guys. Then you have to ask yourself, is the perturbation, is the off-diagonal matrix element of the perturbation equal to 0? So, and this I can write like this. That's another way of writing it, right? That's the matrix, it's a matrix element. And so I have to ask, is that matrix element 0? So if yes, if that matrix element is 0, the matrix element that couples the H prime, and this is in the degenerate subspace. So before answering that question, if I'm asking you to find the energy of state number 5, I have to look to see what is the matrix element connecting state number 5, the matrix element of H prime connecting state number 5 to what other states? What states are the problem?
6.
That's right. I got to worry about state 6, but I also got to worry about state 7, because those are the degenerate ones. Do I have to worry about the coupling of state 5 to all these other guys up above and below? Do I worry about that? Yes or no?
No.
That's right. We don't worry about it because those terms don't diverge in the perturbation expansion. It's only in the degenerate subspace. So if H prime, so I got to look at that off-diagonal matrix element in the degenerate subspace, and if it's 0, then what do I do? What do I do next?
If it's 0, then we don't have a problem, right? If
Exactly. Right, then we just use the formula. Then there's no problem. That's exactly right. There's no problem. And we just use our perturbation formulas. Just use the formulas. But if no, which means that the off-diagonal matrix element does not equal 0 in the degenerate subspace, if this is true, then you have a big problem. And what do we have to do? If that H prime, if the off-diagonal matrix element of H prime, basically, the matrix element connecting different states within the degenerate subspace is not 0, then our perturbation expansion does blow up. It diverges. That's a big problem. What do we do? What do we do to fix it?
We diagonalize H prime in the degenerate subspace.
Exactly. That's exactly right. Must diagonalize H prime in the degenerate subspace and use those states. So what that means is that the old states in the degenerate subspace get turned into new states. You somehow have to find new states. I'll put a bar. That bar means that these are the diagonal, these are the eigenstates of H prime, eigenstates of H prime in degenerate subspace. And once you find those eigenstates by hook or crook, somehow you got to find them, then for degenerate perturbation theory, then the formulas work. Because because then your divergence goes away. And so then you can use your formulas again. You can use the perturbation formula. So let's go back to the perturbation formulas. And we see that then what we'll do is we'll plug in for degenerate states, we'll plug in the new diagonalized states here in the formula. And we don't go to the second order. We'll just stop there. Stop here for degenerate case. And then for the eigenstates, again, we'll stop here. We won't go there. We'll stop here for the degenerate case, but we will use here the new diagonal, the new eigenstates of H prime. Okay, that's degenerate perturbation theory. So that's the algorithm. Okay, and I just want to point out that this quantity, which is the energy, the first order energy correction, that is none other than the eigenvalue of H prime in the degenerate subspace. That's exactly what that quantity is. And if that's not clear to you, then play around with it until it is, or ask me or Carl more about it if that doesn't make sense. Okay, so that's how it works. And so now let's do an example. And there are many examples, but I'm gonna do this one. This is one of my favorites. Let's talk about covalent bonding. I think covalent bonding is a great example of degenerate perturbation theory, because you guys have all heard of covalent bonding and you learned about it. And I know everyone learned, like, I have my my 2 atoms, and I have my bonding orbital, right? Bonding. And then you have I don't know, I learned this in high school. I thought everybody did, but maybe you didn't, I don't know. And you have the anti-bonding. I mean, I remember learning this in high school, but never understanding what it meant. And I think that a lot of people learn this. So, but it's like the most fundamental thing in chemistry. And so I think it's worth trying to understand a little more deeply. So what's the quantum mechanics of covalent bonding, of this bonding and anti-bonding business that everyone's always talking about? Okay, so I think the best way to understand this topic is with degenerate perturbation theory. And so let's consider this problem. So I'm going to give you a problem. Let's consider 2 atoms. And it could be like hydrogen atoms. It could be any 2 atoms, carbon atoms, anything, right? Uranium atoms, whatever. And so consider 2 atoms far apart. And they're far apart. And so then this is the way to picture it. I have some coordinate system, X, Y, Z. And so here's one atom, and it has like a Coulomb potential, and it's sitting here at position R1. And then there's another atom here, and it's sitting at position R2. Okay, my coordinate system. And so I will call this atom 1, and I will call that atom 2. And so let's suppose that if they're far apart, then if we have what are the states for one electron? What are states for one electron? So just think of them as bare nuclei. Think of these as bare nuclei. And so we have these two bare nuclei far apart, and we have one electron, and we want to know what are the states of the one electron. And so in atom number 1, which is this, positive charge here, this is atom number 1, then we think of it like this. There's some atomic orbital here, and I'll call that phi 1 of R. Okay, that's a function. It's an atomic orbital. And then for the other atom, number 2, I have a positive nuclei, and it also has some atomic orbital, phi 2 of R. So, and both of these atomic orbitals have this, let's assume they have the same energy, because the atoms are identical atoms. And so they all have the same energy, E naught, these orbitals. Okay, so that's the situation. And there's only one electron. So the electron can either live in atom 1 or it can live in atom 2. And if it lives in atom 1, it's sitting in that state. And if it lives in atom 2, it's sitting in that state. Okay, and so that describes the situation of H naught. So H naught is just your regular hydrogen Hamiltonian for the, it's just the hydrogen Hamiltonian for the two atoms. Okay, that's H naught. But now, and H naught is when they're far apart. That's H naught. But now what we do is let's bring them closer. Now let's bring them closer together. And now there's a perturbation because when they're close together, the idea is this: I have suppose that my electron is sitting in this one. E minus is sitting here in phi 1, but now the other atom, the other bare nuclei, and remember there's only one electron. This is not a multi-electron problem, it's only one electron. So this one doesn't have an electron. So this is atom 1 and this is atom 2. The electron is sitting in its atomic orbital in atom 1, but I bring the other atom really close, atom 2. I'm asking now, what is the perturbation? There is a perturbation. What is it? And this perturbation is very important because this is the perturbation that causes chemical bonding, which is what holds us all together. Without this, we would fall apart. So what is it?
Is it Coulomb or Coulomb potential? Like that's the extra bit for the.
Yeah, I have electrons sitting in atom 1. So what's the perturbation is coming from what?
Like the Coulomb potential from the second atom?
Yes, exactly. That's exactly right. H prime equals the tug of nuclei number 2. It's the tug, the Coulomb tug, or pull, or whatever you want to call it, right? It's being tugged. That's exactly right. The other nuclei comes along, and that electron, which is happily sitting there, goes, oh, I'm being tugged by the other guy. That's the perturbation. So it's that tug and I'm not even going to write a formula for it, because to do this problem, you don't really need to write formulas for it, but you can imagine that there is some complex formula for it, because I could write the Coulomb repulsion of the other nuclei, it's E squared over 4 pi epsilon naught, the distance between the electron, R minus R2, the location of R2. Okay, so that's the perturbation. It's the tug from the other guy. Okay, but I'm just gonna call it H prime for now. I'm gonna keep it kind of abstract. So that's H prime. So now the question is, what are the eigenenergies and eigenstates? What are the new eigenenergies and eigenstates of the system that arise due to this perturbation? Okay, that's the deal. And so this is how we set it up. So what we do is we say, okay, I have two, so I have H naught, and my H naught, my unperturbed eigenstates. How many unperturbed eigenstates are there? So I want to do that little list. You know how I always like to draw the little lines. So I want to draw the little lines right now. So how many little lines am I going to draw for the unperturbed states of this system? How many? How many states? How many unperturbed states do I have?
An infinite number of them, right?
Well,
An infinite number of possible ones, but only one of them is being occupied, I guess.
well, what I've done for this problem, and this is what we often do, and so this is like a trick. Maybe you haven't seen this trick before, but what we like to do in quantum mechanics, is we always are trying to restrict the number of states that we're working with, because that makes the problem easier. So this is a common trick, a common technique in quantum mechanics. We're always trying to limit the Hilbert space, make it smaller, because then it's easier. So we always are trying to solve an easier problem. So you are correct. There is an infinite number of states. You're totally right. But for the sake of making this problem easier, let's try to restrict our Hilbert space. And so now go through that exercise in your mind and now answer my question: how many states?
Would it be 2?
Yes,
No,
exactly.
one.
Two, because the electron can either be on the left atom or the right atom. Two states, two unperturbed states. Because remember, for the unperturbed states, they're far apart. The atoms are far apart, and the electron can't feel each other. Maybe I should have said that. They can't feel each other. The atoms are far apart. So think of it like this: I have two bare nuclei. I have one electron. How many states can that electron live in? He can either live on the left atom, or he could be on the right atom. 2 states. So that's it. So there are 2 unperturbed states. I'll draw them as 2 lines. Are they degenerate? Yes or no?
Yes.
Good. They are degenerate, and they're living at this state. I'll put a comma there. It's E naught. They're at E naught, and this state corresponds to phi 1, and this state corresponds to phi 2. These atomic orbitals. I haven't even told you which atomic orbitals they are. It doesn't matter. This is a general discussion. We're going to solve covalent bonding in a very general fashion. Okay, those are my unperturbed states. Yeah.
You just ignore. I mean, you said we wanted to constrict the system as much as possible, but it seems that we're just ignoring all the states within each atom, though. Like, can we?
Sure. Why not? We can. And part of the reason we can is, remember, those atomic orbitals, like, for example, let's talk about hydrogen. So remember, it's only the orbitals that are close in energy that really feel each other, because from the perturbation expansion, we know that states far away in energy don't really have much influence because of the denominator in the perturbation expansion. Remember, I told you about that? And so this chemical bonding happens more strongly for states that are degenerate in energy. So for hydrogen, we have the s orbitals at the bottom, the ground state. And so it's really those two guys that are going to do all of this bonding stuff. The other orbitals, the same thing is happening for the other orbitals, but it all happens simultaneously. And so if we can just, so a way to think about it is that all the orbitals are doing this bonding trick at the same time, but we only have to solve the problem for one pair, because it's only the pairs at the same energies that matter, and they're all doing it. But let's just solve it for one case and then generalize to all the other ones. Okay.
I have a question. So, I mean, for covalent bonding, isn't it 2 electrons that kind of share the same state? And then you said in this case, we're just kind of worrying about 1.
This is a tricky point, and this is confusing. But when we talk about bonding and antibonding, it's a 1 electron problem, and we're going to derive the states, and we're going to derive a bonding and an antibonding state. But then in the real world, if we have 2 atoms, there'll be 2 electrons. And so what we're going to do is we're going to have the 2 electrons go in to the bonding state. We're going to occupy the state with the 2 electrons. Because remember how we do many body physics. First, we solve the single electron problem. And then if we have multiple electrons, we just fill up the states. Do you see what I'm saying? So it's sort of like before it's like we would solve the, it's not working, hold on, I'm sorry. Is it still working? Oh yeah, okay. Can you see the drawing on the board? Can you see it?
Yeah, we
New
can.
drop.
So, okay, but I just want to finish. I'm sorry, my computer's distracting me. But I just want to say, you know, this is an important point. Like, remember when I always do the particle in a box and I say, what happens if I take 3 electrons and I throw them into the box? Well, we've done that many times in class. And so the point is, we first do single particle quantum mechanics to get the box. Then we take the multiple electrons and fill them in. So when we're solving the bonding problem of bonding and antibonding orbitals, basically we're trying to find the eigenstates of this new box. Everything is a box to me. And so I have 2 nuclei, and those 2 nuclei form a box. So I'm saying, so basically I'm asking you, what are the states of that box? And then if we have multiple electrons, we'll just fill them in. Okay? But to find the states of the box, it's a single particle problem. And this is a very important point. So, you know, if that doesn't make sense, then maybe we can talk about it after class. Okay.
Professor?
So, yeah.
It's a quick question. We are also disregarding spin degeneracy for
Yes.
for now?
Yeah. Forget spin.
Okay, yeah.
When we throw the particles into the new box, then we have to worry about spin, because eventually we will have to anti-symmetrize, you know, the many-body wave function. And that's why covalent bonds always are singlets, if you think about it. But let's not worry about that. Let's find the states of the box. Okay, so we have H naught, we have the 2 degenerate states, and we got this perturbation, and let's turn on the perturbation. Then we're going to do perturbation theory. So turn on the perturbation, and then what happens? And so I want to know, basically, we want to know what are the new states and what are the new eigenenergies, right? And so so what you should say, so how do we find them? So what you should say is, well, let's use perturbation theory. I got a perturbation. It's the tug of the nearby nuclei. And let's use perturbation theory. And I have little formulas that I can plug into, so it makes me very happy. But before I can use perturbation theory, I have to ask a question. And the first question I ask is what? What's the first question I have to ask before I can use
Is the
perturbation?
state degenerate?
Yes, good. Are the states degenerate that I care about? And these are the two I care about. I want to know how those two states change because they're interacting, you know, with the perturbation. So I'm asking you now, are the states degenerate?
Yeah.
That's right. So then you go, oh no, they're degenerate. Okay, well maybe that's okay because I will now ask the second question. And what's the second question?
Are the off-diagonal elements of the H prime matrix 0?
Exactly. And so that means that these are phi 1, H prime, phi 2. And does it equal 0? Question mark. Now, this one is sort of a little harder to answer because I haven't really, you know, talked about, you know, the functional form of H prime, but let's just consider it sort of intuitively. I mean, here I have, you know, a state phi 1, and then here I have a nearby atom, and I have the state phi 2, and now I brought them close enough so that they can kind of start to overlap. You can see the overlap region, overlap. And so you can kind of see how there's this overlap region, and now I have an electron in the one state, and it's being pulled on by this Coulomb force, right? And so I have here, there's going to be an E squared over R minus, say, R2. And so I will just ask you, if I have this state, and then I have this state, and then I put an E squared over R minus R2, where this is 1 and this is 2, do you think that that's going to be 0? Is there any reason why that should be 0?
When
Justin?
R equals to R2?
No, because it doesn't, because the two atoms are not on top of each other. They're next to each other. You know, it's a bond. We're talking about, you know, what happens when atoms get close to each other. They're not on top of each other. So what I want you to see is that this, and I don't want to belabor this point by getting too into it because it's kind of a waste of time, but I want you to sort of get an intuitive feel that it's not 0. Because, you know, it's like the electron is in this one state and it's being tugged on by a nearby atom, and there's no symmetry, there's nothing, there's no cancellation, there's no reason for it to cancel and go to 0. So there's like no natural symmetry to this situation. You know, we can just say, oh, because of, you know, rotational symmetry, it goes to 0. There is no rotational symmetry here. You know, the atoms are like on a line. So there's no symmetry. So no symmetry. And so as a result, H prime 1, 2 does not equal 0. Okay, so the off-diagonal and matrix elements don't equal 0 of H prime. And so that means you're screwed. Okay, you're screwed, because then formulas don't work. They diverge, right? And so you must find the eigenstates of H prime. So then let's do that. So this is how we find the eigenstates of H prime. Let's find the eigenstates of H prime. So we have our unperturbed basis. Which is this. I have my 2 atomic orbitals of the 2 atoms which are next to each other. And what I do is I first have to ask, what is the dimension of my Hilbert space? Somebody tell me. Say it. What?
2-dimensional.
Exactly. I have 2 basis states, so I have a 2-dimensional Hilbert space. So that means that H prime is going to be, what is the dimension of the H prime matrix?
2-dimensional.
2 by 2, exactly. And so that means I know that my matrix is going to look like this: H11, H12, H21, H22. If there were 3 states, it would have been 3 by 3, but there's only 2. And so I label my states, and I'll call it's, you know, kind of an obvious labeling, but sometimes the labeling is not so obvious, but this time it's obvious. I'll call the state number 1, state number 1, I'll call state number 2, state number 2. So, and so that means then that I got to now construct the matrix elements. And so H11 is going to equal, it's going to look like this. It's going to H prime in the middle, and then there's going to be a state on the left and a state on the right. Okay, what goes on the left for H11 or H prime 11? What goes on the left? Say it.
I1.
Of phi1,
Yes. And what goes on the right?
phi2.
That's right. Now let's construct H prime 2, 2. I'm doing a little out of order. Okay, what goes on the left? Which one? What goes on the left?
Phi2.
Exactly. And on the right?
Phi2.
Phi2 as well.
Exactly. And now let's construct H prime 1, 2.
Hey, Professor, shouldn't the first one be phi1 on the right as well?
Yeah, it should. Thanks for spotting that. Okay, what goes on the left for this one?
Phi1?
And what goes on the right?
Phi2.
Exactly. You see the pattern. This is how you do it. This is the algorithm. Okay, so now we have to calculate these 4 matrix elements. Now we're not going to actually calculate them, but we're just going to notice that, you know, you can kind of know how to calculate them. You know, you would just plug in this. In principle, you could calculate them, you know, like I wrote up here. You know, you would plug in the Coulomb potential and you would integrate the states and blah, blah, blah. You would do all that, but let's not bother. But let's just notice that if, let's call this one alpha, it's going to be some energy. It's a matrix element of a Hamiltonian, so it's going to be some energy. The units are energy, alpha. And how about H prime 2, 2? What do you think is the relationship between H prime 1, 1 and H prime 2, 2 from symmetry?
They're the same.
Yeah, they have to be the same. I think that's pretty clear if you think about it. They got to be the same from symmetry. So that will also be alpha. Now, H prime 1, 2 is going to be a different number, and that's going to be a little harder to calculate because, you know, it's like the state on the left and the state on the right and that tug between. So it's going to be beta. Let's call it beta. I want to ask you a question. What is the sign of beta? Positive or negative? Sign of beta. Remember, the beta, this off-diagonal matrix element means, like, the way to picture it is like that the electron is sitting in state 1, is being tugged on by the other nuclei, and then I'm integrating it with state 2. But the electron is being, remember, H prime is a pulling, right? The electron is being pulled by H prime. So what is the sign of beta? What is the sign of an energy representing a pulling, a tugging? Tell me.
A positive?
Well, look, if I have two charges with the same sign, and what is the potential energy between them? Positive or negative? They both have the same sign of charge. What?
It's positive.
Do they attract or repel?
They repel.
Right. So the positive energy I associate with repulsion. What do I associate? And now I have a proton and an electron. The charges are opposite, and they attract. So what is the sign of the energy if the charges are opposite?
A negative.
Right. So I want you in your mind to associate attraction with negative energy and repulsion with positive energy. So I will ask you again, what is the sign of beta?
Since it's attraction, it should be negative.
That's right. And by symmetry, H prime 2, 1 is also equal to beta. Okay, so that's what we know. And we don't know alpha and beta, but we kind of know that, we sort of know the structure, and we know that beta is negative. So let's not worry about the actual magnitudes, but now we have our matrix. It's alpha, beta, beta, alpha. That's the matrix. And so now we have to to diagonalize it. And so let's diagonalize it. And so we have to say that, remember, H, how do you do the eigenvalue formula? You say H psi is equal to lambda psi. And so then you say H minus the identity matrix times lambda psi equals 0, right? I'm just reminding you of your linear algebra. And if that's true, then you know then that the determinant of that must be H minus lambda I must be equal to 0. And so then that's our eigenvalue equation. You've all done this. You might not remember it because you might not have done it for a while, but you all remember it. And so let's solve that equation. It's alpha minus lambda, beta, beta, alpha minus lambda, determinant equals 0, right? You've all done this. Or I hope you have. If you haven't, then you've got a problem. You better go and learn it. So it should look vaguely familiar to you. Let me see where are the little equations that I have written down for myself so I don't screw it up. Okay, yeah. So then we solve this matrix or this determinant by doing the cross multiplication business. And so we have alpha squared plus lambda squared minus 2 alpha lambda minus beta squared equals 0. Okay, so that's just the determinant. I'm calculating that. And so then I do the little trick using the quadratic formula. So from the quadratic formula, I see that my eigenenergy lambda is equal to, it's going to be 2 alpha plus or minus, it's just the quadratic formula, 4 alpha squared minus 4 alpha squared minus beta squared. And and if that's not obvious to you, it's okay. Just think about it a little bit and you'll see that this is pretty simple. I'm just skipping some steps, but they're very simple steps. And so when you do this algebra, you can do the algebra very easily. And you see that it equals alpha plus or minus beta. Okay, that's it. We just solved this simple quadratic formula. Okay, so those are our eigenenergies. So then what we see then is that this is telling us then that the energies, the perturbed energies, remember, are equal to E naught plus the first order correction, which is equal to E naught. And then the first order correction are these eigenenergies. It's going to be plus alpha plus or minus beta. So I have so my new eigenenergies, my new energies are E plus minus is equal to E naught plus alpha plus minus beta. And now let's see, so I have two new energies, and now I see the old energies were degenerate, those two lines, and they split. Which energy is on the bottom?
E plus.
Exactly. This is the plus state, and on the top is the minus state. And that's because beta is negative. That's why I mentioned that to you. So the plus state is lower in energy, the minus state is higher in energy. And the splitting, what's the splitting? What's the splitting?
2 beta.
That's right. And so that's the splitting. And so this state we're going to call the bonding orbital, and this state we're going to call the anti-bonding. And that's the energies. We just calculated it. It's these alphas and betas, these matrix elements. Okay, and so now let's find the actual states. Now let's find the states. And so that's just the eigenvalues. That's just the eigenstates. And so let's find the eigenstates. And so the eigenstates are going to be, let's find the eigenstates. So to find the eigenstates, we got to do the trick. We got to do the eigenvalue trick. Alpha, beta, beta, alpha. That's the H prime matrix times some unknown eigenvector AB is equal to lambda, the eigenvalue, times that vector AB. And so let's just do the top part. And you've all done this. It's a pain, but you've done it. So the top matrix multiplication tells me alpha A plus beta B is equal to lambda A. And then of course I'll get the bottom one, which is beta A plus alpha B is equal to lambda B. But it turns out I only need this top equation. It's really simple. And so then I can just plug in, let's see, so I have my lambda is, then I'll plug in lambda is equal to alpha plus or minus beta. And so this gives me then alpha A plus beta B is equal to alpha A plus or minus beta A. And now we notice that the alpha A's cancel. And so then, and the betas cancel. And so this tells me that B is equal to plus or minus A. And so what that means then is that my eigenstate psi plus, which is equal to the state AB, is going to be equal to the plus solution. And the plus solution is when B equals plus A. And so that's the same as A. And if I normalize that, then that state has to be 1 over square root of 2 times 1, 1. Okay. And then psi minus is equal to AB, but now B equals minus A. And so that's equal to A minus A. If I normalize it, it will be 1 over square root of 2, 1 minus 1. Now, what does this mean? Well, we know that the state AB, what does that mean, the state AB? Well, AB just means A times phi, it's just shorthand for A times phi 1 plus B times phi 2. So that means that state psi plus is equal to 1 over square root of 2 times 1, 1 is going to be phi 1 plus phi 2. And psi minus is 1 over square root of 2 phi 1 minus phi 2. And this we call the bonding orbital. And this we call the antibonding. Okay, I sort of went through that fast, because I don't want to waste too much time on the math, but okay, we have to move on now. So that's covalent bonding for you using degenerate perturbation theory. We just kind of worked through the whole detail. Okay, so now what we're going to do is we're going to move on to the fine structure of hydrogen. Fine structure of hydrogen. And so the fine structure of hydrogen, so this is kind of a new topic, but we're going to utilize all of the knowledge of perturbation theory that we've just developed. And so the fine structure of hydrogen, the idea here is that in hydrogen, you guys did hydrogen last semester, and so you have an electron that's circling a proton, and you guys, solve it like this. We write the potential. V of R is a 1 over R potential, and then we, you guys solved all the energy levels, right? And this was n equals 1, n equals 2, n equals 3. You solved it all. And so you know that you solved it for H naught is equal to kinetic energy plus potential energy. For the hydrogen atom was negative h bar squared over 2m del squared. And the potential energy was the Coulomb over 4 pi epsilon naught r, right? And then you solved it. H naught psi is equal to E psi. You solved it last semester. And the answer that you got is that psi NLM of R is equal to some radial functions NL times some spherical functions YLM. And the energy was negative 13.6 EV divided by n squared. So you guys did all that. And what were these radial functions? You guys remember what they're called? The radial functions. They have a name. Does anybody remember what they're called?
Harmonics, something.
That was the angular function, the theta phi. What's the name of the theta phi function? The YLMs.
Spherical harmonics?
Exactly. So these are the spherical harmonics. But what about the radial functions? They have a different name. What are they called? Okay, well, I don't expect you to remember everything.
The associated Legendre polynomials or something.
I think, I don't know, that might be, I mean, I think there might be different names for it, but the name that I remember is the Laguerre polynomials. I think they're the Laguerre polynomials, but, actually, I don't remember. Who cares? Whatever. You look it up in a book, So they're called something. So I was curious to see if anyone knew what they're called. I can barely remember myself. But this is the point. The point is not what they're called, but the point is that they exist and they have this structure. And so let's add spin. And so if we add spin, then the most straightforward simple basis is going to be this. If we add spin, then we would just add this S ms, right? That's spin. But we notice that for a single electron, S is always the same. It never changes. So we can just ignore that. And the only one we care about is ms, because that's the one that's either up or down, right? And so the simplest basis for electrons living in an atom, the basis that you guys derived is this, psi n L M sub L M sub S, okay? That's the simplest basis. And in your mind, you should sort of think of it, there's a radial part times, this is actually sort of how I like to think of it. Let's see. Well, there's a radial part times an angular part times a spin part, M sub S. Okay, so N, L, L, M, S. Okay, so that's the basis that you guys know. That's the simplest basis. Okay, so now what we're going to do is we're going to realize that what you learned last semester is this is not the whole story. Because when somebody told you that hydrogen is just this guy, the electron spinning around, that's actually true. But when they told you this Hamiltonian H naught is equal to this kinetic energy plus this Coulomb potential, 4 pi epsilon naught r, that's incomplete. It turns out they were not telling you the whole story. They were only telling you part of the story. So there's a lot of stuff that got left out. Can you think of any of the things that are left out by this unperturbed Hamiltonian?
The inter-electronic interactions.
Wait, let me just write this. The stuff that got missed are, okay, what?
The interaction between, oh no, there's only one electron.
Yeah, let's just talk about one atom. We're just talking about one hydrogen atom. But this missed a lot of stuff. Can you think of any?
Relativity.
Spin coupling.
That's right. Good. Relativity. Spin orbit coupling. That's right. Spin orbit coupling. And there's other things. The coupling to the nuclear spin. That's called hyperfine. Hyperfine. And then what happens if there's if somebody turns on an electric field somewhere nearby? What if there's an E field nearby? What if there's a B field nearby? This we call Stark, the Stark shift. And this we call Zeeman, the Zeeman term, the Zeeman energy. Okay, so all of these things got missed. That's a lot of stuff. And so what we're going to do is we're going to go through these things one by one. We're going to do each of these, okay? We're going to do all four of these things. Not today, but to deal with these things, so the question is, how does this affect the atomic energy levels? How affect atomic energies? And the way that we're going to figure that out is using perturbation theory. And there's something I want to stress. I want to stress that this is called the fine structure of hydrogen. And something that we're going to go through this, but something that I want to stress is that this is not just an exercise to learn perturbation theory, all right? It is an exercise to learn perturbation theory, but it's much more than that, because the energy level shifts that we're about to derive for the next few lectures are very important. They actually have important consequences in every field. They have important consequences in atomic physics, important consequences in condensed matter, solid state physics, important consequences in chemistry, and important consequences in biology. All right, so this is very significant. So these energy corrections have huge consequences in every field of science, because these energy level corrections determine the properties of matter. So if I have some crystal, crystal might be blue or it might be green, and the reason it's blue instead of green might be because of the relativistic correction or the hyperfine coupling or something. That I just want to emphasize that these energies that you missed last semester and that we're going to talk about now are very consequential for basic fundamental atomic physics, chemistry, condensed matter physics, biology. All right, so that's it. Let's now calculate all these corrections. So let's do it. And so let's start with the very first one, which is that relativistic correction. Relativistic correction. Let's do the relativistic correction. And the relativistic correction comes from the fact that last semester, you ignored relativity. Shame on you. You ignored it. And so now we can't ignore it anymore. So last semester, you had an H naught, which was kinetic energy, P squared over 2m, plus negative E squared over 4 pi epsilon naught. Well, I'm not even going to write that. I'm just going to write it like this. I'm just going to say plus V of R. But now what we have is that you use this as your kinetic energy term. But it turns out that for a free particle, that's the wrong energy. That's the wrong kinetic energy. For a free particle, we have E squared equals P squared C squared plus M squared C to the fourth, right? And so we know that the energy of a free particle is the square root of P squared C squared plus M squared C to the fourth. Let me make sure I'm not screwing this up. And we know that this is equal to, that this energy we can think of, if we want to think in terms of kinetic energy, we can think of this as kinetic energy plus the rest mass energy, rest mass. because that's the definition of kinetic energy. Total energy is kinetic energy plus the rest mass energy for a free particle. And so the definition of kinetic energy is E minus mc squared. And so the correct term for kinetic energy is going to be square root of p squared c squared plus m squared c to the 4 minus mc squared. Okay, that's the right term. That's the right term for kinetic energy, and you did not use that. And of course, the reason you didn't use it is because that's a pretty ugly thing, you know. Nobody wants to deal with that, or most people don't. And so that's a pretty ugly formula. I mean, you know, p squared over 2m is much simpler, but this is the correct kinetic energy. And so now what we want to do is we want to fix your screw up. You screwed it up last semester, you did the wrong one, but now we want to fix it. So now we want to find the correction. We want to find the correct energy levels to the hydrogen atom, which takes this into account. And so we're going to use perturbation theory. And so to use perturbation theory, we have to find the perturbation. And so to find the perturbation, let's take a closer look at this equation. And so let's notice that the correct kinetic energy, taking into account relativity, I just want to say the whole point is relativity. We're taking into account relativity. So the kinetic energy, let's take a closer look at this little square root formula, and let's notice that we can write it like this: mc squared times the square root of 1 plus p over mc, just a few lines of algebra, squared minus 1. Okay, so these things are the same. You can see that if you look hard enough. But now we're going to do a little trick, because we're going to notice that we're going to do a Taylor expansion, because we're going to notice that the kinetic energy is equal to mc squared, and then it's going to be here. I'm going to have this term, the minus 1 is minus 1, but this term I'm going to Taylor expand. And it turns out I can Taylor expand that. And when I Taylor expand it, it looks like this: 1 plus 1/2 p over mc squared minus 1/8 p over mc to the 4th plus ... I'm not going to go out any further. But now when I do that, I see that the kinetic energy, the correct kinetic energy, this term cancels with this term. And so I see that my kinetic energy is p squared over 2m, that should look familiar, minus p to the 4th over 8 m cubed c squared plus ... And look at that, that's pretty cool. I think it's really simple, you know, and it's pretty cool. And it shows that the kinetic energy taking into account relativity is equal to our old friend, p squared over 2m. But then there's another term that we missed, minus p to the 4th over 8m cubed c squared. And then there's a bunch of other terms. But this term is this one is the biggest correction. And so what we're just going to consider that one and forget about all the others. And so what we're going to do is we're going to assume from a perturbation theory perspective that h prime is equal to minus p to the 4th over 8m cubed c squared. So in order to take into account relativity that we forgot, we're going to use perturbation theory, and we're going to let that term be our perturbation. And so now the question is, how do the energy levels of hydrogen change? How do the energy levels change? And so we're going to look at all the hydrogen energy levels, and we're going to actually the energy levels, we're going to look at all the states and we're going to ask how do the energy levels change. Okay, and so let's consider a state. Let's consider an arbitrary state, psi n l m sub l, and I could just write m sub s there too. Now, so what is the unperturbed energy of this state? What is the unperturbed energy of this arbitrary atomic orbital? Somebody tell me.
Minus 13.6 times divided by n square.
Perfect.
EV.
Exactly. Thank you. And so now I'm asking you, that is the energy of this level. And so now I'm asking you, how does it change? How does it change due to relativity? In other words, I'm saying, how does it change due to the fact that I have this new perturbation, minus p to the 4th over 8m cubed c squared? I want to use perturbation theory, okay? So that's how it changes, is I got to do perturbation theory. But to do perturbation theory, I first have to check. I have to ask myself some questions. What's the first question I asked?
Do I have degenerate states?
Yes. Is it degenerate? Is psi n l m sub l m sub s degenerate? What's the answer?
Yes.
Yeah, that's correct. It's massively degenerate. I mean, it's hugely degenerate. I mean, I have all these states. You know, this is n equals 1, n equals 2, n equals 3. Now, for n equals 1, I have L has to be 0. But for n equals 2, I can have L equals 0, and I can also have L equals what?
1.
That's right. But if L equals 1, then that means I can have M sub L is equal to plus 1, 0, minus 1. Now for n equals 3, I have I can have L equals 0, L equals 1, and L equals 2. And then you see there's lots of M sub L's, lots of M sub L's. And so in general, for the nth level, do you guys know there's a cute little formula? What's the degeneracy? The degeneracy of the nth level is equal to what?
Isn't it 2n squared?
That's right. And that takes into account spin. That's exactly right. So that's huge degeneracy. So if I have like the n equals 3 level, n squared is 9 times 2 is 18. There's 18 states in the n equals 3 level. Huge degeneracy. Okay, that's a problem. So then what's the next question that we have to ask ourselves? What's the next question? Yeah.
Are the cross diagonal elements? Are they
Right.
0 or not?
Exactly. What is the value of H prime Mn in the degenerate subspace? All right, that's what we have to ask ourselves, where H prime Mn is equal to the unperturbed M state, H prime, and the unperturbed N state. Okay, so is that off-diagonal matrix element 0 or not? And that has huge consequences. We hope it's 0 because then life is simple. So there's different ways to check this. Okay, now we're going to try to figure this out. Now there's sort of a clever, there's like some elegant mathematical tricks that we will use in the future to figure this out. But right now, I just want to do it by brute force. I'm a big believer in brute force because brute force is tedious but easy, rather than elegant mathematics, which is simple but hard to understand. So let's use brute force because it's easier to understand. So brute force, let's answer this question using brute force. And so basically, That's what we do is we just construct the most general matrix element in the degenerate subspace, and we calculate it. Okay, so here it is. So in the degenerate subspace, we know that we have H prime on one side, and we have one state here, psi n. On this side, I'll call it psi NLM. And on this side, what do the indices have to be? I'm calculating a matrix element, and I'm asking you, what do these indices have to be to make this the most general matrix element of H prime within the degenerate subspace? And I'll give you a hint. The subscript on the right-hand side, it is some type of L, N, and L, and M. But I will ask you, and H prime has no spin. Remember, H prime is proportional to P to the fourth. There's no spin here, so we're going to ignore spin. It just sort of falls out. But I will ask you now, on the right-hand side, is N the same? Yes or no?
Yes.
Right, because it's a degenerate. It's in the degenerate subspace. So that means that these N's have to be the same N. That's the definition of a degenerate subspace in atomic physics. Okay, how about the L? Does the L have to be the same in the degenerate subspace?
No.
That's right. In the most general case, it's not the same. How about the M? Is that the same?
No.
Exactly, because those are the things that change. So to have an off-diagonal matrix element in the degenerate subspace means, by definition, that the M's are the same, but there's some difference in the L's and the M's, because that's what's different in the degenerate subspace, are the L's and the M's. So this is the most general off-diagonal matrix element in the degenerate subspace of H prime. So let's calculate it. Let's calculate it. And it's not that hard. It's a little bit hard, but let's do it. So psi NLM is this. It's going to be, I have my radial component. I have my angular component. I'll call it LM for shorthand. And then I have my H prime, which is minus P to the fourth over 8M cubed C squared. And on this side, I have the angular part, which is arbitrary. And then I have my RNL, where the N's are the same, but the L's are different in general. Okay, so you see I'm sort of using this Brockett shorthand to make the algebra easier to write. And so then let's keep going. And then let's notice that this is equal to this. And let's notice, without having to rewrite all that stuff, let's notice that this thing in the middle is P squared over 2M, our old friend that we know about, squared, times some stuff, a negative 1 over 2MC squared. Okay, so I just rewrote it. I'm just rewriting it, a little algebra. And now we're going to do a trick. Now we're going to do a real trick. This is equal to negative 1 over 2MC squared. But now I'm going to do a trick. I'm going to write it all out. On the left, I have the angular part, the radial part times the angular part. But now I'm going to do a big trick. I noticed that this is kinetic energy, P squared over 2M. That's the kinetic energy for the atomic physics problem. Now, you did this last semester. And so I'm going to take a result from last semester, which is actually kind of a complicated result. But I'm not going to go through all the math because it's quite tedious, and you did it all last semester. Hopefully, it will look vaguely familiar to you. The kinetic energy term in spherical coordinates for atomic physics is this. It's negative h bar squared over 2m. When we write it out in all its glory in spherical coordinates, 1 over r squared times ddr. And we were hoping you never have to see this again. Sorry. Here it is. It's coming back. That's the radial part, and then there's the angular part of the kinetic energy term, which turns out can be the orbital angular momentum operator squared. Remember that? divided by 2mr squared. Okay, so it's this thing squared, L prime M prime times R n L prime. Okay, that's what it is. So and this is something that you did in great detail last semester. I hope it looks vaguely familiar to you. All right, so these are the same thing. And now this is nice because now what I can do is I look at this, and this term hits this term, and what does the L squared turn into? Can someone tell me what it turns into?
H bar square times L prime into L prime plus 1.
That's right. Because this is an eigenstate of that operator. And so that means that this state now hits that operator, and the operator turns into that. But what happens when the L prime M prime hits this operator? Does this operator act on L prime M prime? I'm asking a question, yes or no?
Yes.
Well, are there any radial components in L prime M prime?
Oh, no.
There are not. And so does this act on L prime M prime?
No.
Because L prime M prime is a spherical harmonic, right? This is a Y, L, M, theta, phi. It only has theta, it only has angular components. So basically it slides through. And so then what happens is what we get, what we get then is you see that we get this is equal to -1 over 2 mc squared. The theta part slides through, and so we end up with L m L prime M prime times R n L, and then I got this stuff here goes inside there, and this is R n L prime. Okay, so this thing reduces to this expression. And what is this equal to? What is it equal to? Tell me.
0.
Why?
Since they are orthogonal states.
That's right. 0. Because the definition of the off-diagonal matrix element in the degenerate subspace means that at least one of these two indices has to be different. Otherwise, because we're talking about different states in the degenerate subspace. So something in those indices have to be different. So then that and those are orthogonal states. So this thing has to equal 0. So that means that the off-diagonal matrix elements in the degenerate subspace for this particular H prime equals 0. That's good. Yay. That means that now we can use our perturbation formula. So that means then that the simple perturbation formula works. Simple formula works. And the simple formula is simply that now that means that the difference in energy for the nth state that has L and M is going to be now the first order correction. It'll be psi n L M H prime psi n L M. Okay, where these are the unperturbed states. But I'm not going to put the little zeros there because it's just understood they're the atomic orbitals, the unperturbed states. And so I can just calculate this. So let's just calculate it. So I'm going to calculate it like this. I'm going to write it as -1 over 2 mc squared. And I'm going to have psi nlm. And then I'm going to do a trick to make the math a little easier. I'm going to still use that kinetic energy trick, the old kinetic energy squared. So this is just a clever way of calculating this matrix element, which is actually sort of hard to calculate, but that's a way that I can write H prime. And now I'm going to do a cute little trick, because what I'm going to notice is that I'm going to use a little trick, and I'm going to notice that the old Hamiltonian H naught was equal to P squared over 2m plus V, the potential energy for the Coulomb potential for the hydrogen atom. So that means then that P squared over 2m is equal to H naught minus V, where this is the Coulomb term. And what that means then is if I square this, so this is a really cute little trick that once I show it to you, it's really easy, but it's the kind of thing you would have never thought of on your own until someone shows it to you. This is equal to H naught squared minus H naught V minus VH naught plus V squared, right? And then what I can do is I can plug this now into here. And so now I have that the delta E NLM is equal to -1 over 2 MC squared. And I have psi NLM, and I have H naught squared minus H naught V minus VH naught plus V squared, psi NLM. Now, the reason why we went through this trouble is because the psi NLMs are eigenstates of H naught. And so what does that mean? H naught turns into what now? What does H naught turn into? Well, we're running out of time, so I guess I've just got to speed this up. H naught is the unperturbed energy. It's just the E naught N. That's just the 13.6 electron volts divided by N squared. And it's this thing squared, right? And that H naught is going to be E naught N. And that H naught is going to turn into E naught N. And this V goes as 1 over R, and this V squared goes as 1 over R squared. And so that means that to calculate this energy correction, what I'm going to have is this. I'm going to have this is -1 over 2 MC squared times E naught N. When I say E naught N, I just mean the 13.6 divided by N squared minus 2 E naught N times E squared over 4 pi epsilon naught when you just go through the math, and then this is going to be times psi NLM 1 over R psi NLM plus E squared over 4 pi epsilon naught squared psi NLM 1 over R squared psi NLM. And it turns out that you can figure these terms can be figured out from problems in the book, problems 7.15 and 7.42. And then when you go through all the math, then you see that the energy NLM is equal to negative E naught N squared over 2 MC squared times 4N over L plus 1/2 minus 3. And so what you see is that and so we use the word that it splits the L's. It removes, so the word we use is we say that it removes the L degeneracy. In other words, if I have a bunch of states that are degenerate, it splits them. This is energy. This is L1, L2, L3, and this will be L1, L2, L3. It splits them in energy. Okay, so that's all that we'll say for now. Sorry for going over. and I'll see you next time. Bye-bye.
Thank you, Professor.
Okay.